Hello, welcome everybody. This video is on chapter 5 and it talks about electromagnetism and leads up into the discovery of the Bohr model of the atom. Okay, so the first thing I need to lay down is just what is electromagnetic radiation and basically what are wave properties. So electromagnetic radiation is just a whole spectrum of different types of light, ranging from, say, radio waves all the way up to gamma rays. So in the spectrum, we have different energies of light that have different wave properties of, say, wavelength or frequency. So let me just describe those first. Frequency is the number of cycles per second a wave travels, and the wavelength is the distance traveled in one cycle. I show that here. So basically, a high frequency wave moves fast and it has a shorter wavelength. So the wavelength is peak to peak. Here I have a lower frequency wave or light, and basically this has a longer wavelength. So you see they're inverse. Lower frequency, longer wavelength, higher frequency, shorter wavelength. So just think about higher frequency, higher energy. That's something that you will need to just intuitively get in touch with. The other thing that I just want to bring up is speed of light, just because it comes up in one section. This is how fast the wave can travel in a vacuum. So 3 × 10⁸ meters per second. Any constants that you use during the section will be given to you on an exam. Okay, so there are a couple phenomena I need to explain to you that led up to the discovery of the model of the atom. And these are notable phenomena because they couldn't be explained by classical physics. For example, classical physics can describe rainbows, how those are made. But there are a couple phenomena that can't be explained. And it just really opened up the box to how we needed to think about how electrons move in an atom and what that arrangement is. So the first is the photoelectric effect. So what I want to draw your attention to is this chamber here. There's a vacuum, so meaning nothing's in here except this metal plate. And there's an electrode here, a positive electrode. So what's happening in this experiment is you have a metal, and just think about that. A metal's composed of atoms of some sort of metal. What is that composed of? What's inside an atom? You guys know this: protons, neutrons, and electrons. So if you can add enough energy to an atom, you can actually kick out electrons because electrons are more on the outside. We've already seen electrons being removed from an atom, say sodium metal going to sodium plus, it lost an electron. So that's exactly what we're doing here. We're kicking out electrons from the metal. Where are those electrons going to go? Well, they're negatively charged, so they're going to flow to this more positively charged electrode, and then that could be read as a current as the electron moves towards the positive electrode. So this is what this experiment is. Light is shined on this piece of metal, and if there's enough energy in this light, it can eject an electron. So that's measured. So basically what the scientists were doing was determining whether a current is flowing or not. What's interesting though, and what came out of this, was that not all light was the same. So you might shine, for example, a blue light or a red light or another type of light, and not all of them would produce a current. Not all of them had the right energy to eject an electron. They also flipped out the metals. They used different metals. So they found out different metals have a different minimum frequency. So remember, higher frequency, higher energy, different minimum frequency of light that was needed to eject the electron. So that was really confusing to scientists. Einstein came up with an idea and he said, light is actually what's called quantized into certain bundles or packets of energy, and he calls those photons. So basically, he said light isn't this continuous diffuse thing with just this broad spectrum of light, broad spectrum of energy, but basically it had a specific energy. That's why certain lights that are shined on those metals, not all of them can eject the electron. So he called these photons. And another way to think about it is maybe light isn't just a wave. Maybe it's like this pellet or particle, a little photon that's shot, and like billiard balls kicking out an electron from that metal surface. But overall, Einstein relates light to being quantized. And then the other thing to always remember is that the light has a certain energy that's related to its frequency. So you can have a certain photon of light and it has a specific energy. There was some work done by Max Planck, which basically showed that it was some multiple, the energy of a photon of light is some multiple of, some constant times its frequency. H became known as Planck's constant, is given this number. It's in units of joules times seconds. Frequency is cycles per second, so it's units of per second, or hertz per second, or second inverse seconds is also given the units of hertz. So joules times seconds divided by seconds gives you an energy of joules. The other thing is we know there's a relationship, as I showed on the previous slide, between speed of light, frequency, and wavelength. So another way to write this equation is, instead of nu, you could relate that to, or substitute it with c over lambda, and lambda is wavelength. So just to be clear, this italicized v is called nu and its frequency. This lambda, Greek symbol, is the symbol for wavelength. So sometimes we do want to find the energies of a photon of light. If you're given frequency, you can use E equals h nu and use that equation. Or if you're given wavelength, you can use E equals hc divided by lambda. Okay, the second phenomena I want to talk about is just what's called the atomic line spectrum. So there's another experiment that can be done where you take a gas in a tube and you electrically excite it. Then you filter that light through a slit and shine it through a prism, and that means all those visible waves of light can be separated and can be projected onto a film. So when we do this with a hydrogen atom, what we see is 4 very specific bands of light. We don't see all the colors of the rainbow. And we always see these 4 for hydrogen. It's like a fingerprint. If you look at other elements such as mercury or strontium, you see other bands, but a different fingerprint. Why would that be? That was a little confusing to scientists at the time as well. What helped explain that was a model by Niels Bohr. So this is Niels Bohr, and what he said was that electrons are actually moving around the nucleus in a fixed orbit, and that the lowest energy state, we call it the ground state, all other states are excited, and the farther you go from the nucleus, the higher the energy. So I'm going to show you the Bohr model, and we're going to bring that back to the atomic line spectrum. So basically, the Bohr model tells us that not only are the electrons moving in an orbit, in fixed orbits around the nucleus, but those orbits are quantized. Just like Einstein said, the energy of a photon of light is quantized in specific packets. It's not this continuous thing. This is saying that the energy of electrons, where they reside around the atom, they're in very discrete levels. Okay, so quantized just means a very specific level. And there's a certain very specific energy required to move them from one level to another. So let me just tell you first, and then I'll show you the model. If you go from a lower to higher state, you need energy. So you need to absorb a photon. If you go from a higher to lower state, a photon is emitted or energy is released. and this energy of the photon is related to the change in energy of the atoms. Here's our model. This is the nucleus. These are the orbits around the nucleus. We start at the ground state, n equals 1. That's the lowest energy. It's the lowest energy because the negatively charged electron is closest to the positively charged nucleus. This is the biggest attraction. This is what makes up atoms. The electron is attracted to the protons in the nucleus. The next level is n equals 2. So this is higher in energy because you've pulled that electron away from the nucleus. I like to call my electron Ed, and he's pulled away from his beloved proton Penelope. So it takes energy to rip him away from his beloved Penelope. There's an n equals 3, 4, 5, 6, 7, etc., all the way to infinity. So basically, the light that we see for hydrogen has to do with these transitions. So we know that hydrogen only has one electron, but where is that electron? Usually it's closest to the nucleus in the n equals 1 ground state. But if somehow you add energy, electrically excite it, shine a light, it can jump to another level, maybe n equals 2 or n equals 3 or 4 or 5. Maybe it has enough energy to jump or be completely removed from the atom, then that's when you get a cation. So the light that we're seeing is basically an electron in a higher level going back down to a lower level. So this can happen from any level going to any lower level. So for example, if I go from n equals 6 to n equals 2, I already told you these are very specific energy levels. These are quantized, meaning there isn't something in between. The electron can only be in these white circles. It can't be here in this dark space. So going from n equals 6 to n equals 2, that's a very specific movement from 6 to 2, and that releases energy because you're going from a higher to lower, going back closer to the positively charged nucleus. Think about it as like a ball, or a ball on a spring, or a ball on a rubber band being pulled out. If you let it go, it wants to go back to closer to the center. So that specific transition has a specific energy. For us, that energy of that particular wave, or the photon being emitted or released, is the color purple to our eyes. Going from n equals 5 to n equals 2 releases a photon of light that corresponds to us being able to see it as blue. And then 4 to 2 is green, 3 to 2 is red. What about going back to 1? That actually releases a ton of energy. And so going from, say, n equals 5 to 1, that's such a high energy, we don't see that as color with our eyes. That's only seen by UV. It's in the UV series. So if you translate this here, we have an energy diagram here on the right. And let's say I'm at a high level, say 4 or 5 or 6, and I release all the way down to the ground state, n equals 1, you can see how much energy is released. If I'm only going to n equals 2, I release less, but that's the range that's visible to us as color. Going to level 3, releasing back down to n equals 3, that's seen in the infrared region. So just again, when you see light and light's emitted, that's when you go from a higher to a lower state. Energy is released. However, if you go from lower to higher, that requires energy, and it's because you're ripping out the electron away from the positively charged nucleus. So the other thing I want to point out is that anything away from the nucleus, it has higher potential energy. Just think about it again as a ball on a rubber band, or a ball on a string being stretched out, or say even like a basketball being put really high up in the air. It has this potential energy, and then later if it drops back down, it releases energy. So anything higher out or further out has higher potential energy. Anything closer to the nucleus or at the ground state is the lowest energy there. Okay, There's been a lot of work done to calculate those energies going between different energy levels. You can use the Bohr equation for the hydrogen atom, and here's an equation here. Again, if I want you to use this, I'll give you this equation on an exam, but you'd have to know how to use it. This says this number here, minus 2.18 times 10 to the minus 18 joules times this, which is 1 over n final squared minus 1 over n initial squared. So n final is where you end up at. So say if we calculated the energy for an electron in the n equals 4 level, we returning to the ground state. So that means n initial is 4. So 4 squared is 16. So 1 over 16 here. And then returning to the ground state. Ground state is not n equals 0, it's n equals 1. So this is 1 over 1. So this would be 1 minus 1 over 16 and then multiply by this number. Okay, what if you want to completely ionize or remove an electron, generate the cation? Here you let n final equal infinity. It's out away from the nucleus. So then when you have your n final as infinity, infinity squared is infinity, but 1 over infinity goes to 0. So it's just the positive of this number here. And hopefully that makes sense. It requires the energy. That should be a positive number. It requires the energy to rip a nucleus out of its, I'm sorry, rip an electron out of the nucleus. Okay, so let's just bring this all back together. The photon of light is being released when you go from a higher to a lower level. Or if you're going from a lower to higher, that same photon of light is absorbed. Because to move an electron from lower to higher, you need energy, and it'll get that energy from the light. However, if it's at a higher excited state and goes lower, it's going to release that energy. So the change in energy of the atom is the energy of that photon. So say if you observed the photon, the blue photon, when the electron transition, the energy of that blue photon of light, you can relate that to h nu. Maybe you knew the frequency of the blue light. So you could actually calculate the energy of the photon of light, knowing its frequency times Planck's constant, and you could figure out the energy of that transition going from 5 to 2. The other thing I just want to mention, just this common theme that we've been seeing, anytime you see delta E, delta H, delta T, it's always final minus initial. So for example, delta E would be the final energy minus the initial energy. So if I was again talking about, let's say, the blue light being observed, that means an electron went from n equals 5 to n equals 2. Delta E could also be determined just by knowing the energy of the n equals 2 level minus the energy of the n equals 5 level. So sometimes we have an idea what those energy levels are and the energies for those levels. Okay, I just want to tie this in and close out this video with just how this is observed in nature. So there's something called bioluminescence, and some of you may have seen this already. But basically, bioluminescence is light given off by a living organism. Here, this is a fish, and you can see that its spine and other parts of its body is illuminated. This happens when there's a chemical inside that organism, and when it's excited and goes back down to its ground state, it can emit a light that's observed. So that's what is seen. We see this in certain glowworms. Here, this is a San Diego surfer. So sometimes we have red tide, and basically there are algae blooms that have this bioluminescence. So basically, if you ever go down to the beach, and I know some of you have seen this, maybe even surfed in it, but basically you can see the waves crash, and all of that agitation is just setting off the bioluminescence, and you can see that. And I've actually been in the water trying to see that and paddling around, and it's really truly one of the most amazing things I've ever experienced personally in my life, just having the hand go through the water and light light up the ocean like that. Don't swallow the water because sometimes the blooms can be a little toxic, not always around California, but other areas. Here's a squid, here's a fungus here. Okay, there's one last one I want to tell you about. This is luminol. So this is a structure of a chemical, and this is called a bond line structure. So the lines are a bond, but if there's no atom shown, a vertex here, you assume that's carbon with enough hydrogens to make 4 bonds. So basically, this is a structure. You don't need to know this, but I just wanted to show you when this is excited, its electrons can drop back down to its ground state and emit a light. This is important because this is what's used for forensics. So you've probably seen a number of crime shows where they spray down a crime scene. What they're actually spraying down is luminol and some sort of oxidant. So there is a redox reaction going on, and basically iron, just the Fe, and it's Fe2+, I believe, in the blood that catalyzes the luminescence for luminol. So what's really cool about this is that it can detect trace amounts. So that's why even when people clean up their crime scenes, you can still spray this luminol, the oxidant, and it can detect even trace amounts of blood that have been left behind. One limitation is that bleach actually lights up everything. So that's why if you need to cover up a crime scene, just make sure you're covering it really nicely with a lot of bleach. All right, I'm going to end here, and we'll take a closer look at exactly, maybe not exactly, but a high probability of where the electrons are in the atom.